Okay, so welcome back. Um, Before I get started, we didn't have lecture on Friday. I was gonna upload a replacement lecture over the weekend, but then I was looking at basically the rest of the semester and what we still have to cover, and I realized that we're gonna cover everything anyway, even if I don't replace that lecture. So I decided not to do it, but I reserve the right to, if I feel like, in one of the subsequent lectures we end up maybe not going as fast as I originally thought, then I reserve the right to post, some like supplemental lecture at some point. Obviously, when I do that, I'll let you all know. As someone mentioned, last Wednesday's lecture is actually not viewable. So that's a mistake. That's just because after last Wednesday's lecture, I forgot to make it public rather than leaving it unlisted. So I'll do that right after this lecture is over, so you'll be able to see that. So I apologize for that. If in general, in the future, if you're unable to view a lecture and it's been, a day and a half, 2 days after the lecture, just send me an email because that's what has happened. Every now and then, YouTube is really, really slow at uploading stuff, but I haven't had an issue like that since the summer. So over the summer, it was actually terrible because my lectures were requiring like almost 24 hours to upload, which was no good. Anyway, so that is the deal. Well, the supplemental lecture won't necessarily be over the weekend. It will just be, it will just be made whenever. Anyway, so gonna need some F's in the chat because I got a positive COVID test this weekend, which was the reason why I canceled Friday's lecture because I was resting and didn't think I had it in me to lecture. My voice didn't sound too good, but anyway, so hopefully that won't affect anything else going forward. But if I get if I get unreasonably sick, then I will make arrangements, and there will be lectures continuing on in some fashion. So it shouldn't be too big of a deal. So anyway, I'm feeling fine. Yeah. So anyway, so with that said, eigenvalues and eigenvectors. This was also the thing that made me heavily tend toward not wanting to upload this as a supplemental lecture is unfortunately every time I end up needing to upload a supplemental lecture, it's like it's like the first day we've spent on something that's important, and I don't want to relegate it to a supplemental lecture. So in this case, that's very much how it is. Eigenvalues and eigenvectors are very important, and especially the first bit of them. So I had mentioned last time that the idea is, my main motivation is I have a matrix A, and ultimately I want to be able to understand matrix iterates. So raising A to the nth power, that is multiplying A by itself a bunch. And we saw that this is actually pretty terrible in general. And so our understanding eigenvalues and eigenvectors allows us to talk about this in a much better way. And so what is the definition of an eigenvector and an eigenvalue? So definition. Okay, so an eigenvector an eigenvector of an n by n matrix A this is something that confuses students a lot. So it is necessarily non-zero. We'll see why intuitively we want this to be the case. So this is a non-zero vector x, okay, such that a times x is equal to lambda times x for some number lambda. Okay. Now, the textbook for this definition calls lambda a scalar here. Again, you know what scalar means. I'm intentionally going to call it a number here, and I'm not going to say anything more about it. Okay. A number is a scalar when we want it to be, and it's a different kind of scalar when we want it to be a different kind of scalar. So you'll see what I mean when we get to the end of this chapter. But just so that I don't have to make some kind of new definition for eigenvector, I'm calling this a number lambda. Okay, so lambda, so this lambda is called the eigenvalue for A associated to the eigenvector, say x. Actually, this lambda is called the eigenvalue for A associated to the eigenvector V if A V is equal to lambda V. Okay. And so there is an association, a correspondence between eigenvalues and eigenvectors. Okay. And so what this means is that basically whenever you think of an eigenvector, there is associated to it some eigenvalue lambda, because there has to be, because there's this equation. So this lambda has to have some value, whatever value that is. That's the eigenvalue associated to that eigenvector. And vice versa, right? So if you have an eigenvalue lambda in this equation, any solution to that equation for that lambda is an eigenvector associated to that lambda. Now, naturally, we could ask, how many eigenvectors can be associated to the same eigenvalue? We'll see that here in a second, because it's actually really easy to do that kind of analysis. But first, I want to see, what is it that this is saying, right? So what does this say? What does this say? Well, so it says my matrix A times a vector V is equal to a number times V, right? Which I can think of as a scalar. This is a scalar times V. And so, for an eigenvector V, my matrix acts like multiplying by a number, right? So, what this says, to quote, is for an eigenvector, so for an eigenvector of A acts like multiplication by a number. Now, why might that be something you care about at all? Well, harking back to this original question I claim we're interested in, if I want to understand, matrix iterates, so A to some n, what better way or what better subcase to be in than if we actually had an object that was kind of sort of acting like just multiplying by real numbers or multiplying by some scalar, because in that case, then doing this n times would just be like raising that thing to the nth power, and raising something to the nth power is really easy, right? So this is, you might see from that, intuitively, why having something that, or having a nice list of all the vectors for which this matrix acts like multiplying by a number is important. Okay. After linear transformation, V will stay on its span if V is an eigenvector. So let's see here. So I mean, what do you mean in the span? So I mean, basically, another way of interpreting this, I guess, would be that you have columns of A written with the weights or the components of V, and that is actually a scalar multiple of the components of V. So I'm not going to say any more about linear transformations and eigenvalues right now, but we'll do that. We'll do that a little bit later. Okay, so anyway, note a few things. So first, note if V is an eigenvector for A with eigenvalue lambda, because remember, every eigenvector has associated eigenvalue. When you mention an eigenvalue, it's natural to talk about some associated eigenvector. And you may have seen this terminology if you've already had Math 246 here, which is, this is called an eigenpair. So many times by an eigenpair, what we mean is an eigenvalue together with an associated eigenvector. Okay. Now, a natural question is how many eigenvectors does some eigenvalue for a matrix have? So this provides an answer. So if V is an eigenvector for A, then so is C times V, where C is a scalar. Okay. All right. So let's say that V is an eigenvector for A. So define, say, V sub 1. So define V sub 1 to be CV. What do I need to check in order to verify that this is actually an eigenvector? Oh, and I should stress it doesn't change the associated eigenvalue either. So if V is an eigenvector for A with associated eigenvalue lambda, then so is CV, and eigenvalue is still lambda. So eigenvalue is still lambda. It's not C lambda or something like that. Okay. And so if I define V sub 1 to be CV, then what do I need to show? I need to show that A times V1 is equal to lambda times V1. So is that the case? Okay, well, let's compute. So A times V1, well, V1 is CV. So this is A times CV. Of course, by those ancient matrix properties that we know, I can pull this constant out. So this is C times AV. But V is an eigenvector for A with eigenvalue lambda. So what's AV? Well, AV is lambda V. So this is C times lambda V. Well, now I can move C back in. So this is lambda times CV. But CV is V1. So this is lambda times V1. And indeed, AV1 is lambda V1. So, okay. So what this means is that eigenvectors are only well defined up to scalar multiplication. What that means is that if you have one eigenvector for some eigenvalue, then any scalar multiple of that thing is also an eigenvector. Now there is, maybe a more complicated question here, which is, is that all of them? And to answer that, we need other considerations. So first of all, let's consider, how do I find these things? All right, so how do I, before I go any further here, how do I find eigenvalues? and eigenvectors for a given matrix A. Okay. So, as I mentioned before, my coverage of this is going to be slightly, it's going to jump around a little bit more than is done in the textbook, but it's exactly the same idea. And so, how do I find eigenvalues and eigenvectors for a given matrix A? Well, let's start out with the basic equation. AX is equal to lambda x. Okay. Okay. And now, let's see, algebraically, what does this mean? Well, if I do a little bit of algebraic manipulation here, if I move lambda x over to the other side, I get ax minus lambda x is equal to the 0 vector. Okay. Okay. Can I simplify this? Well, you might be tempted, if you look at this, you might be tempted to say, yeah, I could simplify this, right? If you're just doing some, you're just quickly doing some algebra here, you might say, look, there we go. There it is. All right, these two things are the same. But does this work? Can I do this? And if not, what's the problem? So if I factor out an x like this, what's the issue? And what is a minus lambda? Well, a is an n by n matrix, but lambda is just a number, right? So this doesn't make any sense, right? A minus lambda makes 0 sense. Okay, you can't subtract a number from a matrix, as was noted in the chat, and so this is no good. Okay, but the spirit of this is still valid. I just need to fix it. Yeah, so someone brought it up in chat. It should be the identity matrix times lambda. So the idea is, what is a way of viewing scalar multiplication, lambda times x, as a matrix multiplication? Well, it would be lambda times the identity, right, times x. So you can check yourself that this is exactly the same, right? So now this is exactly the same as this previous line. Now I can do this factorization perfectly. So this is a minus lambda I times x is equal to the 0 vector. Ah, yes. So this is a very, very important relationship, right? So for a given lambda, any solution to this is an eigenvector associated to lambda. Conversely, to find eigenvalues lambda, we look for values of lambda for which a minus lambda I times x is equal to the 0 vector has non-trivial solutions. But what kind of equation is this? What kind of matrix equation is this? So this is a homogeneous matrix equation. So of course it always has trivial solutions. Right? Now you understand why in our definition for eigenvector we specified that it had to be non-zero. Because otherwise, right, here we would always have the solution x equals 0, and so we would have 0 as an eigenvector for every single matrix. It's just stupid. We could have done that, but it's just not interesting to include that, okay? And it muddies our nice statements we're going to be able to make later. Okay. All right. And so let's revisit this idea. So the idea is I am looking for when this thing has non-trivial solutions, right? And this is what I'm looking for. All right. And so, what is this? What is this thing that I'm actually looking for? Note the set of all such solutions is we have the machinery, we have the terminology to write this set in a nicer form. What's another way we can call this? So the set of all solutions to the equation a minus lambda I x is equal to 0. Does anyone see a way to write that? Yeah, it's the null space, right? It's the null space of that matrix. Okay. This is called the eigenspace associated to lambda. So this is the eigenspace for A associated to the eigenvalue lambda. Okay, so lots of terminology, but hey, it's easy to remember, right? Everything has the prefix eigen, right, which is German for particular. Okay. Okay. Now, going back, what is a convenient way computationally? So what is a convenient way of saying exactly when equation, I don't want to rewrite this, so we'll call it equation star here, like asterisk. So what is a convenient way of saying exactly when equation star must have non-trivial solutions? Now, this is what I'm looking for is a method that doesn't necessarily just answer this for a fixed lambda. I'm also looking for a method that actually tells me, like a list of all possible lambdas for which this could possibly happen. Okay? And the idea here is I have a matrix, right? Like, let's rewrite this. Right? Let's rewrite this as homogeneous equation Cx equals 0. Okay? What is a nice condition when this has non-trivial solutions? So this has non-trivial solutions if and only if what? Yeah, so someone said it in chat, we want it to be non-invertible. What's a very concise way of saying that? Well, we want the determinant of C to be 0. Right? We want the determinant of C to be 0. So that's why I said, what is a convenient way? I mean computationally, right? Yes, so someone said linearly dependent columns. That's also true, but that's also something that follows immediately once you know that the determinant of the matrix is 0. Okay. And so this homogeneous equation has non-trivial solutions if and only if the determinant of this matrix on the left is 0. Okay, and so star, here is the big fact. Okay, and here's what's the difference between the approach I'm using here and what you're going to see in the textbook. The textbook does exactly this same thing, but it leads you into it as if you've never heard of an eigenvalue or eigenvector before, and it leads you into it kind of like it's pretending that it's really trying to motivate everything, but I motivated it in a different way, talking about matrix iterates, and I know that many of you have already seen or at least heard about eigenvalues and eigenvectors before, maybe even computed some in like a differential equations course or something like that, and basically rather than trying to do a bunch of examples that illustrates this, I'm just going to drop all of the theory at once. That way you can just immediately compute all these things. There's no reason to hide what's going on from you behind the scenes. Okay. So, all right. So then, fact, equation star has non-trivial solutions if and only if the determinant of A minus lambda I is equal to 0. Okay, this is the key thing. Okay, again, rather than trying to hide this stuff from you, I'm just going to immediately jump in and tell you exactly what this thing is. Okay. All right. Well, here's a big question. What kind of thing is the determinant of A minus lambda I? Okay, maybe I'll mimic the textbook a little bit here, where I'm just going to pick something here. So let's do a quick example here. Let's see. Let A be the matrix 1, 6, 5, 2. Okay. All right. Then what is A minus lambda I? Well, that's this matrix 1, 6, 5, 2 minus lambda times the identity matrix. Well, this is the 2 by 2 identity, so 1, 0, 0, 1. That's what it looks like. Okay. So Malika, you're saying it's a number. So the determinant of a matrix, of course, is a number. So that's true. It's 100% true. But if lambda is a thing I don't know, right? Here's where it's a little bit more conceptual, where lambda is actually a thing I don't know. It's true for a fixed number. This is just going to be some real number. But for a fixed lambda, it's just a number. But if I don't know what lambda is, if I'm trying to figure out what lambda is, that's what I'm asking. What kind of object is this? So we'll see here in a second. This kind of provides the basic example. And so what does this look like? So this is 1 minus lambda in this slot. So here's 1 minus lambda. So 1 minus lambda. In this slot, I would have 6 minus lambda times 0, so that's just 6. And then in this slot, I would have 5 minus lambda times 0, so that's just 5. And then lastly, I'd have 2 minus lambda. Okay. So here's what A minus lambda I is. So then what's the determinant of A minus lambda I? Well, this is a 2 by 2 matrix. If I compute the determinant of this thing, so this would be 1 minus lambda times 2 minus lambda minus 5 times 6, right? So this is 1 minus lambda times 2 minus lambda minus 30. This is perfectly fine to see what's going on here, but hey, let's just go ahead and write all this out. So if I go ahead and write this out, expanding this, I have 1 times 2, so that's 2. And then I have minus 2 lambda minus 1 lambda, so that's minus 3 lambda plus lambda squared minus 30. And so this is lambda squared minus 3 lambda minus 28. Okay. Now this is a quadratic polynomial, right? It's a quadratic polynomial, and so this is actually a particularly nice one. This one factors, so this is a quadratic polynomial in its factored form. This would be lambda minus 7, lambda plus 4. Right? And so what this says is that the determinant of A minus lambda I being 0 implies that lambda minus 7 times lambda plus 4 is equal to 0, which implies that lambda is 7 or minus 4. These are the eigenvalues for A. So this is how this works. Okay. Now, I didn't really answer my original question. I just went ahead and did this example of how to find eigenvalues, but I didn't actually answer what kind of thing is this. It is always a polynomial. It's a polynomial. Okay. Now, you know that solving polynomials in a nice way becomes, extremely nasty very quickly. In fact, in your whole life, basically the only exhaustive manner of doing this that you've ever come across is the quadratic formula, right? As soon as you're dealing with a generic cubic, you're already a little stuck, right? So, what degree is this polynomial? What size is this polynomial? Well, it depends on the size of A. Okay, this polynomial is so important. It's called the characteristic polynomial. It's a very, very important property, or a very important quantity associated to a matrix. So I'm going to define that now. So here's the definition. So let A be an n by n matrix. The characteristic polynomial so the characteristic polynomial of A is P sub A of lambda. Actually, no. That is not at all the notation I'm going to use. It's P sub A of Z, which is the determinant of A minus Zi. Okay. There's nothing wrong with using lambda as the argument there, so okay, maybe I'll do that just because Pretty sure that's what the textbook does. You'll see later why I am insistent on doing things slightly differently, just because it's a little bit more convenient and I don't have to rename a bunch of stuff later. Okay, so this is called the characteristic polynomial of A. Okay, now what is the major super important fact? Eigenvalues of A are the roots. They're exactly the roots of the characteristic polynomial. Okay. Okay. I.e., another way of saying this is lambda is an eigenvalue of A if and only if the determinant of A minus lambda I is equal to 0, or P sub A of lambda is equal to 0, right? Either way. Okay. Okay. So someone asked, because, for instance, right, unfortunately, the second you start talking about roots of polynomials, well, even in the absolute simplest thing, right, x squared plus 1, right, it's a really, really simple quadratic, but what are the roots of it, right? It has no real roots, right? It only has complex roots, so the only roots are plus minus I, or plus minus square root of minus 1. So what this means is that for a full picture of what's going on, we are eventually going to have to talk about complex numbers. And there are matrices that have complex eigenvalues, even though the matrices in question they don't have complex numbers in them anywhere. They only have real entries, but they have complex eigenvalues. So that's exactly why I've been so guarded about calling lambda a scalar or saying lambda is real. I'm just calling lambda a number, because yes, I'm doing this in preparation for later when there's a possibility that lambda is complex. Okay, so we're going to do that at the end of this chapter, but that's exactly what I'm doing. Okay. Yeah, so someone said the characteristic polynomial can't always be quadratic. Wouldn't it be of order? Yeah, it's degree n for an n by n matrix. So I'm going to list some facts about the characteristic polynomial. So some facts. Some facts about the char poly. So some facts about the characteristic polynomial and polynomials in general. So there are things you might have forgotten, like the fundamental theorem of algebra. So some facts about the characteristic polynomial and polynomials in general. Okay, so I'm just going to rattle off a list of things. So if A is an n by n matrix, then the characteristic polynomial of A has degree n. Right? What does that mean? I mean, it means exactly what you think it means. It means characteristic polynomial looks like lambda to the n plus like a sub n minus 1 lambda to the n minus 1 and so on, right? All the way to a1 lambda plus a naught, the constant term. Okay. Okay. So this leads me to a question. That the answer to this question actually comes from basic algebra, not really linear algebra here, or matrix algebra. And that is, if we've already seen that eigenvalues of A are roots of the characteristic polynomial, and the characteristic polynomial for an n by n matrix has degree n, quick question, for a matrix A that's an n by n, what's the most amount of eigenvalues A can have? So what's the maximum number? So what's the maximum amount of eigenvalues A can have? Well, as someone noted, n. Right, so the answer is n. Why? Well, this is one of these facts from basic algebra that if you have a degree n polynomial, the most solutions it can have or the most roots that it can have is n. Right? Of course, we also know the fundamental theorem of algebra. So what's the fundamental theorem of algebra? Well, the fundamental theorem of algebra tells me that if I'm willing to accept complex numbers, and I do something called counting with multiplicity, right? Then every polynomial has exactly n roots. So counting with multiplicity, we'll talk about this later. So counting with multiplicity and accepting complex roots, then every polynomial of degree n has exactly n roots. Yeah, so someone mentioned in the chat, this is repeated roots, right? This is the notion of repeated roots. So just thinking about this, you might say, wait, this can't possibly be true. In fact, you might immediately come up with a very easy counterexample, right? So here's, let's say, like x minus 1 squared, right? So x minus 1 squared, that's a quadratic. And if I graph it, right, it looks like this. So it has the single root x equals 1. You might say, okay, it's degree 2, but it only has one root. What we do is we count this as two roots. Okay, so they're not distinct, but this would be called a double root. So this would be called a double root, and we would list out the root twice. 1, 1. Right, now that might seem like a silly thing to do, but coming up with this terminology is what allows us to state the fundamental theorem of algebra, which is a really nice statement. It means there's no mystery. You don't have to, normally if you might remember just in the quadratic case, it's already annoying because in the quadratic case, what are your options? How many real roots do you have if you're only concerning yourself with real roots? The answer is either 0, 1, or 2. Right? There's 3 different cases. But counting with multiplicity, this says there's only one case. There's always 2 roots. Right? You either have 2 complex roots, 1 real double root, or 2 real roots. Right? So this is just a nice framework to use. It's convenient. Lets us immediately dispense with any mystery going on here. Okay, and so what's the maximum amount of eigenvalues A can have is n, but fundamental theorem of algebra says if we're willing to accept complex eigenvalues, I'm not going to mention anything else about them right now, we'll talk about them later, But so another way of saying this is basically counting with multiplicity. I'm going to put this in quotes for now because we're not going to practice it right this second. We'll do it here in a little bit because this is going to be important. But counting with multiplicity, a matrix A that is an n by n matrix has n eigenvalues. Okay. Now note, these are not distinct, right, necessarily, right? So this is different, so not, i.e., these are not necessarily distinct. So n distinct eigenvalues. Okay. So that's possible, of course. In fact, when that's true, this is actually like one of the greatest things that can possibly happen in a matrix, is when you have an n by n matrix that is n distinct eigenvalues. This is a really, really nice thing. But counting with multiplicity, we can consider every n by n matrix to have n eigenvalues in this way. Okay. All right, and I think that's a pretty good place to stop. So you might be a little worried here. You might be a little worried because I have talked a lot about eigenvalues here, but it might seem for various purposes that it's the eigenvectors that are important. There's a reason why we can essentially just talk about eigenvalues, because finding eigenvectors associated with some eigenvalue is a relatively straightforward process. So you'll do some examples of that in tomorrow's discussion. So be sure to make it to tomorrow's discussion because there's going to be a good bit of practice with this computational stuff. So we'll see that finding eigenvectors given the eigenvalues is not too bad. And finding the eigenvalues is just solving, it's just finding the roots of a polynomial, which is good in the sense that that is a like completely deterministic process in the sense of like I've now moved you totally out of linear algebra, and so you can either do it or you can't, right? And of course, things are going to be fair, so you're always going to be able to do it. And so basically we have laid the groundwork for all of the computational stuff we need for this. And this is going to let us, basically blaze through the applications of eigenvalues and eigenvectors. So I would say probably, if no more lectures have to be canceled or pushed back or whatever, I would say probably we'll mostly finish our discussion of eigenvalues and eigenvectors by the end of class Friday or maybe next Monday. But anyway, so I will see you all on Wednesday. And like I said, if lectures need to be postponed or supplemented in some way, I would let you know beforehand. So anyway, I will see you all on Wednesday. And if you have any questions before then, you always let me know. Remember, discussion is tomorrow, where you'll be doing some eigenvalue, eigenvector practice stuff. Okay. So anyway, I'll see you all on Wednesday.